So it's quite difficult to come just after Dimitris, but well, I will try. So there will be some overlap with Dimitris' talk. I will present some dynamic predictions from joint models and their evaluation. These developments were motivated mostly by the monitoring of prostate cancer progression after radiation therapy. Indeed, in this kind of cancer, we have a very well-known biomarker of progression, which is the prostate-specific antigen, PSA. And when we want to predict the clinical recurrence of prostate cancer, well, we can use the information we have at diagnosis, that are the initial log PSA measured at the diagnosis, or some scores, such as the Gleason score, aggressiveness score, and the T-stage, the size of the tumor. And in addition, we can add some information about the PSA dynamics. Usually, that will be the last value of PSA, or a summary of PSA dynamics, such as the PSA dynamic time. But if we look at some individual trajectories of PSA over time, so 0 is the end of the treatment for prostate cancer, the log PSA here, and so you have individual trajectories. You can see that for all the patients there is a very important drop in the first year after the end of the treatment, and then a sort of stabilization over time, or some slight rise, more important rise, and very important rises of PSA. If we look at the people who have some clinical recurrence, you can see that, yes, those people are those who have the most important PSA doubling time, rise of PSA. But when we want to take into account this information in the prediction of clinical recurrence, well, we may have some problems. The first thing is that, okay, we see that the rise of PSA may be a predictor of clinical recurrence, but maybe the wrong PSA dynamics would be of importance. The second problem is that, as Dimitris detailed to you, the PSA is an internal covariate, it's not an external covariate, so we have to take that into account. It's measured with error, so you can see well, there are some errors here, and it's collected at discrete time, so we have missing values. And because of that, well, we need to joint model the PSA with these measures and the time to the clinical recurrence. And that's the focus on this talk. I will focus on joint model to compute and evaluate dynamic prognostic tools of clinical recurrence of prostate cancer based on the PSA trajectory. So I will just remind a little bit the principle of joint models, and then I will move on to computation of individual dynamic predictions. I will then introduce how we can evaluate the predictive performances of such dynamic predictions, and I will illustrate on PSA evaluation zones and clinical recurrence of prostate cancer. And then I will open on two extensions from that. The first one is to try to make some predictions that under different scenarios of treatment for the prostate cancer, and also to make some dynamic predictions in the presence of competing risks or multiple events, not just one. So, the joint models. Well, you had a very good introduction with Dimitris, and I will take a slightly different way to introduce that. So, we have a longitudinal biomarker that we are interested in, and we have a time to event. Those two processes, they are linked, they are correlated. And to take into account this correlation, we would assume that a latent structure will capture that. So it will capture the correlation there is between the longitudinal biomarker and the time to event. One way to do that is to assume that the random effects from the longitudinal biomarker model will give this latent structure. And that defines the shared random effects that Dimitris introduced. So here is my notation for this shared random effect model. You have the biomarker Y for subject I at time Tij, which is the occasion, and you define just a linear mixed model for that. So with functions of times, let any function of time associated with some random effect Ui. And you have also some covariates and functions of time that will define the mean trajectory of your biomarker. And then you have the errors. And the idea here is to include some features of this mixed model in the risk of event. We do that using a proportional hazard model, in which, in addition to the standard external covariates, XE, we will include those features of the linear mixed model as a function of the random effects. And this function of the random effects can be multiple. The interest show you a different example. That can be the current level, the current slope, the individual the deviation, the random deviation, or this integrated area under the curve, etc., etc. There is so this kind of model is can be estimated using maximum likelihood framework or Bayesian framework, and you have this very nice R package. In addition to that, well, we can think of other ways to define the latent structure that will capture the link between the longitudinal biomarker and the time to event. And instead of defining some characteristics of the longitudinal marker, you can just imagine that you can divide the population in structures, latent structure, discrete structure, latent classes, latent subgroups, that will be characterized by a certain evolution of the longitudinal biomarker and a certain type to event. And that defines a second type of joint models, the joint latent class models. These models are defined in three submodels. First of all, you define a discrete latent variable, CI, and you assume that this CI is the latent class, so each subject belongs to a certain latent class. You can evaluate the probability of belonging to a certain latent class according to covariates, and then inside each latent class, you define a specific model for your longitudinal outcome and your time to event. This is actually exactly the same as before. It's a linear mixed model with exactly the same idea behind. It's just that the parameters are specific to the latent class. For the time to event, we use also a proportional hazard model, and again, well, it's a very standard proportional hazard model. The idea is just that the parameters for the baseline wave function and possibly for the covariate can be different from a class to another. So here we don't have any feature regarding the linear mixed model and the random effects. All the correlation is captured by this latent class. This kind of model can also be estimated by maximum likelihood in the maximum likelihood framework, and it's implemented in R also. Okay, so now we have different models, joint models, and the idea here, well, you saw that in different ways during those 2 days. So we are interested in predicting the probability of event from a time of prediction S, the landmark time, and within a window of horizon T. So T is the horizon time. And we want to predict the probability of event based on the information we have. So this information is the information at time 0, which are the variables we know as the diagnosis, and the biomarker repeating measures until time S, so noted like that. These biomarker repeating measures, so those are the repeating measures at different times of measurement, those times being lower than the time of prediction. Actually, this probability is exactly the same formula, whatever the joint model. It's actually just based on the decomposition of this conditional probability, but according to the shared latent structure. So in a joint latent class model, well, we will decompose that according to the latent class, and in a shared random effect model, we will decompose that according to the random effect. So basically, we have a conditional probability of having the event between time S and time S plus T, given that we are in a certain latent class. And then we weight that with the probability of belonging to this latent class, given all the information we have collected until that time. We average that over the latent classes. In a shared random effect, it's the same. It's the conditional probability of having the event between the time S and the time S plus T, but this time, given the latent structure, the random effect. And then we multiply that by the density of the Random effects given the information we have collected until this time S, and we integrate it. So exactly the same kind of formula, exactly the same kind of idea. So based on that, well, we have predictions that now we want to provide some dynamic prognostic tools. So in a second time, well, we have to say that, okay, now we have estimated our model. We have theta hat and variance of theta hat. So everything is estimated, and we have a subject I. We collected this information until, let's say, today, time S, and we have the other providers. And then we want to provide a dynamic prognostic tool for him. So we have two strategies. The first one is just to compute that at the NN, at the parameter estimates. And that gives us a point estimate of this predicted probability. But we want to appreciate the variability of this prediction. So to do that, as Virginie yesterday and Dimitris today introduced, we can try to approximate directly the distribution of this probability. And to do that, we use some Monte Carlo approach. We just drew many thetas according to the asymptotic distribution of the parameters, theta hat and the variance of theta hat. And then we can compute those probabilities at each theta t. That way we will be able to have a point estimate using, for example, the median, and we will have 95% bands using the 2.5 percentile and the 97.5 percentile. And that way we can really appreciate the variability of the dynamic predictions. Okay, so here's an example. So we have prostate cancer, so it's a man, and actually had reference at 3 and 8 years. We collected his PSA with 2 measures after the end of the treatment, and so the last one was around 1. So you saw some survival curves in Dimitri's talk. Well, I just here summarize that with the probability of having the event in the next 3 years, and I compute that is something like 0.50. And I did that using a joint model. I could have done that using a standard survival model that did not use this information. That's what I did also. And the idea here is that now I got a new measurement at 1.5 years, and I will update those predictions, and again, and again. So finally, we can just summarize those dynamic predictions using just a single graph with each time the prediction in the next 3 years according to the information we have collected before. So that's the kind of thing that we want to do. The problem is to know if this is good or this is good. We have to evaluate those dynamic predictions. And so we have to we have to answer the question, does the model predict well the event at a time of prediction S? There are many measures to do that. Well, no, there are several measures to do that, and some of them were extended to the setting of dynamic predictions from joint models or from normal analysis. So the first one is to evaluate the discriminative power using the LUC, the sensitivity or specificity, which evaluates the concordance there is between this predicted probability and the expectation. A second one, which is quite well known, is the error of prediction with the Breuer score, which compares directly this predicted probability with the event status. And specifically in joint models, there is a third one which was proposed by Daniel Comanche, which focuses on the prognostic information. It's called the prognostic cross-entropy, PCOC, and it evaluates actually the density, the conditional density of the time to event given the information we have collected. In the next talk, Paul will speak a lot about that and a lot about that. So in my talk, I will focus on this one. But all what I did with this one could be done with that. Okay, whatever the measure you use, you have to be careful with the data you use for validation. Which data should I use? Well, we can use the training data, so the data that we use for the estimation. The problem is that the apparent measures that we will estimate, the single estimators of the measures I presented it would be very, very difficult to do really some consolidation on that. Hopefully, we have an approximation of consolidation that was proposed for parametric models, and so that makes it possible to have a direct computation of those measures by avoiding the time to repeat the consolidation. And that's available for equals and pseudo-Fourier score. The best thing is to evaluate on validation external data, and in that case, just a simple estimate of ROC. In my talk, I will focus on that. Okay, so I will speak about something quite complicated. The name is very complicated. Expected, prognostic, observed, cross-control, deposit. Very complicated, but actually it's quite simple. It's just that we focus on the density of what we are interested in. That means the time to event, based on the fact that we have observed the information about the biomarker and that we are among the subjects still alive, still at risk at time S. So it's just to evaluate the density of the residual time to event, what we want to focus on. When we are on external data, well, we can just approximate that using the log likelihood, the conditional log likelihood of the time to event given the information about the biomarker. And this is computed directly using quite the same formulas as I showed you for the predicted probabilities. It's the same kind of weighted average. When we are on the training data, well, we have to take into account the other optimism, and using the approximative consolidation, it's just that we add a penalty that is derived from the derivatives of this probability and the joint likelihood of the model. So it's it can be directly computed and simply as soon as you have a likelihood so parametric model. This is a risk function, so we want the lower the better. And we can compare the models, well, we can compare the predictive accuracy of those models by computing the difference in this or the difference in this and have a 95% tracking interval. This kind of measure was developed to evaluate the predictiveness in the remaining infinite window of time to event. But you can also censor the information after a certain time to focus on a certain horizon of prediction, let's say at an horizon t. So here is an example. It's an illustration, just 459 subjects. So it's just for the pedagogy. So we have a John Latham class model here and a chaperone effect model here. I wanted to compare those two approaches using exactly the same structure of model. That means the PSA trajectory was in two phases, the short-term drop and the long-term rise. And I assume some model baseline risk function for the time to clinical recurrence. I put covariates everywhere in the models to have and did not do any selections. For the chaperone effect model, I assume a dependency between the PSA repeated measures and the time to clinical recurrence according to the PSA, the level of PSA, and the current slope of PSA, as Dimitri showed you previously. The Bayesian information criterion for the John Latham class model was better than the one from the chaperone effect model. This was quite expected because in the John Latham class model, you define different profiles of trajectory for the biomarker. So you can be very good in fitting this part of the model. But as we discussed before, this is not what we want to do here. We want to focus on the dynamic prediction. So the ability to model the risk of event. So it's not because we had this difference, this important difference, that the predictiveness of this model will be better than this one. So we evaluated that using the EPOS criterion. So here are the curves that we can obtain. We have the time, the landmark time, so the time at which we do the prediction. So for example, at 3 years, I don't know which one is the precise like that, but well, let's say this is the EPOS in the remaining. So the predictiveness in the remaining window of clinical assumes an independence between the PSA prognosis and the time to clinical recurrence. In black, you have the Chevron effect model, and in the different colors, you have the models, the joint contrast model, with different number of latent classes. The red one being the one that we chose. So you can see that all the joint models had a better predictiveness than the model assuming an independence. Well, that was expected because PSA is a predictor of clinical recurrence. And you can see that there is some differences also between joint models. If we look at the difference here, the differences here between ADOS, we can see that in this context, on this data, with the black difference here, the joint latent class model with 4 latent classes was better in predicting the time to recurrence than the Chevron effect model. This is just in this example. Okay, so we could have done that with the Grasser and the AUC, and we could have done that also on external data. That's the kind of thing that we can do to compare the joint models or the joint models with other approaches. But then, so the dynamic predictions that we have developed until now assume that we don't have any change in the follow-up for the subjects. So the subjects, we follow them, and for example, they will not initiate any new treatment or anything in the window of prediction. In practice, for cancers in particular, it's frequent to initiate new treatments. And that's the case with prostate cancer, with the hormonal therapy. The hormonal therapy is initiated in patients to try to delay the time to clinical recurrence. The problem is that it changes the dynamics of the biomarker, and it also changes the risk of clinical recurrence. That's why we do that. And so the dynamic predictions that we would do, that I did previously, can't be used in this context. So the solution is to directly model this initiation of a new treatment and to define some differential dynamic predictions according to the initiation of this treatment. So let's see what it is in practice. We have a subject with these repeated measures until today, type S. He's provided a diagnosis, and we know that he has not initiated any second treatment, yet. The question is, okay, should we initiate any treatment today? Well, to answer that, we can just assume that he would initiate a treatment today and evaluate his probability of having a recurrence in that context. It's just the same predicted probability as before, but now I assume that the time of hormonal therapy to I is now, and I compute his probability of having clinical recurrence. And I can do the same, but assuming that he would not initiate any hormonal therapy in the next 2 years. And in that case, it's just that I assume my conditional probability is conditional on the fact that he will not initiate any hormonal therapy in the future. We did that. We tried to look at that on our data among 2,386 men treated by radiation therapy. For this context, we only use Chevron effect models because to make it possible to make some predictions according to that, we wanted to have different models for the dependency that we had between I, YI, and the time of clinical recurrence. And the Chevron effect model was a nice solution for that. So the dependence in the proportion of our model was not only on the random effects, but on the time of initiation. And we tried different ways to take into account this dependency. For example, we assume that the current level of PSA and the slope of PSA before and after hormonal therapy had the same effect, with a change in the risk of clinical recurrence at initiation of hormonal therapy. We tried also to stratify those effects before and after hormonal therapy. We tried also to make a dependence between PSA and clinical recurrence based on the hormone effects, with a change in risk at the time of hormonal therapy, etc., etc. The problem here is that we want to evaluate those predictions, and to do that, we have to split the validation in 2 parts. We have to evaluate the predictability of that and the predictability of that. So we have to do a differential evaluation of the predictive performances. In the absence of hormonal therapy, we can do it exactly in the same way as previously. We can compute the epoxy curve or the Bryer-Scott curve at different times of predictions with a certain horizon. That's what we do with an horizon of 3 years. But after immediate hormonal therapy, the problem is that the time of prediction S is different for each subject. So at each time of prediction, we will have only one observation. So we don't provide a curve for that. So what we did instead was to average the epoxy computed for each subject over the dry distribution. So we will have just 1 point. Okay, here are the results. So in black, so it's the epoxy curve, so the time of the landmark time, the time of prediction, and you have different models. So in black, the one that assumes an independence between the PSA measures and the time to clinical reference. In blue, the one that are based on the current level and the current slope of PSA. In pink, the one that stratifies this effect on the initiation of hormonal therapy. And finally, in red, another one based on the Randall effects, a dependency on the Randall effect. So you can see some differences, and those differences are finally important because you see that the difference 0 here is largely is not in the interval, and is largely outside the interval. So you can see some differences. This one having the best predictive performances, the one based on the Randall effects. If we look at now what happened after immediate hormonal therapy initiation. So as I told you, what we have to do is to integrate that and obtain just one single value. Those are these values. So the values for the model that assumes no association between the PSA2 measures. The classical one with the level and the slope, the effect of the level and the slope of PSA. This one which stratifies the effect before and after hormonal therapy, and the one with the Randall effects. What you can see is this one. It was close to the blue one just before, but now it's close to this one, and actually gives has the same predictiveness as the one based on the Randall effects. So here you can see that the evaluation of the dynamic prediction is not the same based on the scenario that we evaluate. How can we use that in practice? Well, let's say that we have a man with a clinical reference at 2 and 7 years. That was one of the men of the data. And we have these repeated measurements until 2 years. And at 2 years, we want to know what we should do for this man. We can compute his probability of having the event where, in absence of change in his treatment, so in absence of initiation of hormonal therapy. But we can also evaluate his predicted probability of having the event in the next 3 years if he initiated immediately a hormonal therapy. And we can do that again at the next point at 2 and 6 years, after 2 and 6 years. And we can appreciate the difference between that and see if we should initiate a hormonal therapy based on that. Okay, so finally, I wanted also to show you how to introduce another extension of those dynamic predictions from joint models, especially in the presence of competing events, of multiple events. In the concept progression, we don't have just one event of interest. We may have multiple sources of progression: the logarithms, the metastatic recurrences, death. And the problem is that the technical decisions may differ according to the type of progression. So we may not take a composite event and evaluate the prediction of progression that way. We may want more to distinguish between those different types of progression. And to do that, well, the solution is to extend the joint models to include some competing events and multiple events. And then we can provide some individual dynamic cause-specific predictions. So basically, we have still a joint model, shared Randall effect model, general focus model, and the idea is just that now the event may have multiple causes, or you could think of multiple events also. So eta is the close-up event, and what we want to predict now is the predicted probability of having the event between the time s and the time s plus t, but given that the event will be of full scale. And again, it's according to the information we have about the biomarker until the time s. This can be derived from any model, and Paul will present you an example of that just after the break. So to conclude, I wanted today to show how we could derive from dynamic predictions from any joint model, and I would say any landmark analysis also. Those dynamic predictions are potentially more accurate because we can systematically update those dynamic predictions according to the information we have collected dynamically. And there is a nice example online done by Jeremy Taylor, which provides on the website. You input your data and the PSLT measures and etc. And you can have some graphs to evaluate the prediction of the clinical returns, but also the dynamics of your PSA. So that can be that's the kind of thing that we can expect to do using those joint models. I wanted just to give a caution here, which is that those dynamic predictions should be based on a large amount of data. I should do an illustration of 459 subjects. That's not it. It was just for an illustration. With those dynamic predictions, as usual, we need really to evaluate the predictive accuracy. And well, this is essential in any prognostic tool development. The problem of over-optimism is maybe really important in complex models. That's why we should either use the cross-validation technique on training data or use external data. There are several available measurements, so I focused here on the EPOC, but we have also the error of prediction, the discrimination with the discriminative forward with the LUC. And again, I wanted to put a caution here. So I should do some Bayesian information tutorial and some evaluation of the predictive accuracy. When we focus on dynamic predictions, we should not look so much. We should not base our conclusions on the goodness of its measures, because the goodness of the measures are really changed by the goodness of the longitudinal part. When we want to focus on predictions, we want to focus on the survival part. And so I saw in different examples here, for example, in the second example, the model giving the best goodness of it were clearly not the one giving the best predictive accuracy. This is also because we focus on a certain time s, and so we don't have all the subjects at that time of prediction. If we want to predict after 3 years, 4 years, 7 years, it will not be, the amount of information will not be the same as in the whole goodness of it measures. Using joint models, well, we saw today with Dimitris and maybe this presentation that it provides a flexible framework for predictions. We can have multiple specifications between joint Laplace model and shared random effect models, but also within shared random effect models. This can be extended to evaluate different scenarios of treatment, with the caution here that this example was on observational studies, so we may have, we probably have an indication bias for the treatment. But this can also be extended to multivariate events or multivariate biomarkers, etc., etc. It's just a framework. So finally, I wanted to thank my collaborators, and especially in the ISPED. And if you want some details about what I presented, there are some papers. Thank you very much.